All right, folks, welcome back. We're in our CCIE routing and switching mentorship program. We are now going to be kind of taking a deeper dive, and not quite as deep as some of the next couple of lessons after this, but we're going to be taking a look at some more Dmvpn configurations. We'll be taking a look at some other Dmvpn strategies. We did our introduction to Dmvpn the last time, which I thought was a relatively good introduction in relation to what are some of the basic characteristics of Dmvpn, what are some of the moving parts and so on with regard to GRE and Nhrp and so on. So we're basically right here. We just did this lesson the last time. And so what we're going to cover in this lesson here, or actually in this section, are these three lessons. Now I know it says 2 hours and 1 hour and 1.5 hours, but there's a lot of overlap between these individual topics that I would normally record kind of over a time, lengthy time period. So what I've done is I've kind of gone through and streamlined the discussion a little bit. A lot of the stuff we did talk about in the overview section, we'll do a quick review on some of that stuff. And I've kind of just consolidated all of this so that we can make sure that we kind of get through these topics. And then what I'm going to end up doing for the next lesson is most likely kind of combining this section here, which is going to include things like what are some of the design considerations for EIGRP over Dmvpn phase 1, what are some of the design considerations of OSPF under Dmvpn phase 1, and so on, BGP, and we'll even take a look at some on-demand routing stuff as well. Okay. So this time we're going to focus primarily on Dmvpn phase 1, and we're going to focus on implementing Nhrp over that Dmvpn. We'll talk a little bit about some of the characteristics of Nhrp as part of that process. All right. So what is Dmvpn? We did talk about that in our last discussion. We did take quite a few notes on Dmvpn concepts, right, regarding the hub and the spokes, what the components were of Dmvpn versus the overlay versus underlay network. What are some of the key differences between Dmvpn phase 1, phase 2, and phase 3, and so on. All right. So why do we use Dmvpn? How does Dmvpn work? How is it different than, say, running a bunch of point-to-point connections versus point-to-multipoint or layer 3 over this VPN? What is the logical hub and spoke topology? How do we support direct spoke-to-spoke traffic? Right? We did talk about that in our previous lesson as well, which indicated that direct spoke-to-spoke traffic was going to be able to happen in Dmvpn phase 2 and phase 3. And we can see here that that's identified here. Spoke-to-spoke communication is permitted. And as well as spoke-to-spoke communication is permitted here. We didn't put that in here specifically, but it's kind of assumed, given that Dmvpn phase 3 is the next generation, if you will, of Dmvpn phase 1 and phase 2. All right. So we're going to kind of get into some of the specifics. In this case, we are going to look at some command line, some debugs, we'll do some packet captures, we'll take a look at some of the frame formats that we talked about in the last discussion of Dmvpn. So we are going to get into the actual configuration. For the exam, you're going to pretty much, both the written and the lab, you're pretty much going to have to be familiar with all phases of Dmvpn. But there really isn't that much of a difference. There's only a couple of commands that separate Dmvpn phase 1 from Dmvpn phase 3. Now the functionality and some of the design considerations can be significantly different. And as we go into some of our future lessons, that's what we're going to focus our attention on. Overall, though, the end result of a Dmvpn hub and spoke network is that we have reachability between the hub and we have reachability between the spokes. And relatively simple configuration. I mean, Dmvpn is not really that complicated to configure. However, the implications, probably the biggest implications that you're going to see, is going to be based on how the routing process works over that Dmvpn network, right? And that's really where all the key design considerations come into play. all the way from RIP routing up to BGP and on-demand routing. And we'll talk about why EIGRP and BGP would probably be the preferred routing options for a DMVPN network, why OSPF doesn't really fit. If we don't get into it in this lesson, we'll certainly talk about that in a lot more detail in the next lesson when we start to get into some of the other routing protocol configurations over DMVPN Phase 1. From our previous discussion, we also learned that DMVPN is a combination of multi-point GRE, generic route encapsulation, the next hop resolution protocol, which is a critical component to the operation and functionality of DMVPN. These are completely independent operations, by the way. GRE does not have to work in a DMVPN environment. You can do static GRE tunnels between two endpoints without the use of a next hop resolution protocol. But obviously with the dynamic nature of the spokes and how they're able to call home, if you will, having that Nhrp is a critical component. And then also the third piece is, well, there's four pieces technically, right? The third piece is the Ipsec crypto profiles that we're going to apply as an overlay to the DMVPN network to provide that layer or phase 1 and phase 2 cryptography, right? ICKMP and IKE and Ipsec at phase 2 for confidentiality, integrity, and peer authentication. All right, then the fourth thing would be kind of what our focus is going to be on that we didn't talk about as much in the last time is what is the routing protocol that we're going to run over the network. All right, we're going to take a look at how DMVPN works from that routing perspective, and that's where we're going to do our deep dive into the DMVPN technology, what routing technique is best, and so on. So why do we use DMVPN? I think you guys have a pretty good understanding of that from our previous discussion, or even prior to what we even talked about in the last lesson, which is it allows us to establish a secure and dynamic and scalable VPN solution independent of the service provider access method, whether we're using the internet, whether we're using MPLS, or other methods for creating this underlay network that allows the point-to-point connectivity or the point-to-point communication between the DMVPN components, the NHCs and the NHS, right? The next hop server and the next hop clients. We only require basically just general IP connectivity to form the network. And that means that we can actually have a combination of network connectivity. We can have maybe some robust internet connectivity at our corporate location. We can have some cable modem or some small business or medium-sized business internet connectivity at remote locations, or we could simply run DMVPN over a mixed mode environment, right? It could be frame relay, it could be MPLS. It doesn't really matter because our encapsulation occurs at layer 3. And it doesn't even matter if it's an IPv6, IPv6 underlay network, IPv4 underlay network, and we're trying to overlay IPv6 on top of IPv6 or IPv4 on top of IPv6 or IPv6 on top of IPv6. It doesn't really matter, right? Because in the end, GRE will encapsulate anything, even non-IP related traffic. All right. MPLS can be a little bit more difficult if maybe there is a particular site within our topology that's not going to be serviced by the same service provider. So interoperability might be a little bit more challenging, but we can still run this technology over software-defined WANs and other types of WAN technology. In fact, I had a question recently from one of my students online in our Facebook group that said, how is SD-WAN going to affect my routing domain, right? My WAN. How's it going to affect the use of MPLS or frame relay or some of these other technologies? And I said, well, SD-WAN doesn't define a transport protocol. SD-WAN simply defines automation. So it allows us to automatically provision and service our domain, but we can still use the same traditional underlying network technology, okay? The routing policy is also not dictated by the service provider in this case, right? So if we are participating in a layer 3 MPLS VPN or a layer 2 MPLS VPN or some other internet-based WAN topology, we don't need to worry about whether or not the underlying network supports what our routing needs are, because the overlay network is where we apply the routing in this particular case. All we have to ensure is that we have some sort of IP connectivity or IP reachability between the endpoints from the public domain. That's really it. All right, so that's one of the terms that you'll have to be familiar with, right? DMVPN uses both an underlay routing protocol and it uses an overlay routing protocol. The overlay routing protocol is what we're going to run internally, and then the underlay protocol is what we run for reachability, right? So that's the difference between, say, the internet or the backbone connectivity, you know, over the internet or the MPLS cloud or whatnot. That would be the underlay network. And then the overlay network is just going to be simply our tunneled interfaces that provide us the ability to establish a routing protocol over the GRE tunnels. Next hop resolution allows the resolution of the spoke networks and the registration of the dynamic spoke endpoints. And then finally, IPsec on top of that provides the cryptography. DMVPN is highly scalable, but it depends on the design. You know, you can have some bad DMVPN designs that limit its scalability. You could be running legacy versions or obsolete versions of DMVPN, which would disallow point-to-point or multi-point spoke communication that allows that spoke-to-spoke transactional traffic. But you're going to see throughout this lesson and the rest of the lessons that our concern is designing two separate functions of DMVPN. The first function of DMVPN is going to be the control plane functionality, which is typically going to be controlled by the hub. And then the second is the data plane functionality. How do we manage our data plane forwarding? How do we manipulate the data plane path? And that's going to vary depending on the overall design. And that's also going to vary depending on the DMVPN version that you guys decide to run. All right, we're going to talk about all this as we get into more detail in each of the phases. You know, it seems kind of relatively simple with regard to just understanding how DMVPN is configured. But the reason why we have 11 hours or, you know, potentially 11 hours of discussion in this topic is because of all the considerations that have to be taken into account when we're using these modern IGP routing protocols, or even an EGP routing protocol in the form of BGP, you know, incorporating route reflector design and so on, okay? Well, you could potentially have thousands of sites in DMVPN, or you could even have tens of thousands of sites in DMVPN. And I haven't seen tens of thousands of sites, but I have certainly seen DMVPN deployments that have thousands of sites, okay? So how does the DMVPN work? Again, I would encourage you guys to go back and take a look at our original introductory video, because I did get in a whole lot of detail on that topic. But we're going to rehash some of those basic concepts here just as a precursor to kind of getting into our implementation. DMVPN allows essentially a full mesh of tunnels. It's a very simple, you know, kind of very simple templated configuration that we can then kind of extrapolate and apply on all the routers except for one of the routers, right? The only router that's entirely unique, well, I wouldn't say entirely unique, but it definitely has some unique characteristics, is the DMVPN hub, which we also refer to as the Nhrp next hop server. And that's where we're going to focus a lot of our control plane functionality in our DMVPN domain. From a provisioning standpoint, the configuration is actually relatively simple. All right. Now, if I was provisioning, say, regular IPsec point-to-point or regular GRE point-to-point tunnels, I would definitely have scalability issues, right? That n times n minus 1 divided by 2 formula that we use to identify exponential scalability in a point-to-point design. And we don't have to worry about that in this case because of the tunnel configuration using the multi-point GRE interface for all of our connections. The tunnels themselves, they do get created as an on-demand circuit between the nodes. The only ones that are permanent are the tunnels that go from the spoke routers to the hub routers, right? Those are the only tunnels that are permanent. All right, as far as the spoke-to-spoke communication goes, the spoke-to-spoke communication is dynamic, and those are definitely on-demand circuits that are only going to be established and maintained while traffic is flowing from one spoke to the other. Once that traffic stops after a certain time, keep alives are going to expire, and those spoke-to-spoke tunnels will be removed until they're needed again in the future, right? And that's the nature of the spoke-to-spoke communication. That behavior does not change regardless of the DMVPN phase, right? Phase 1, phase 2, phase 3. Well, certainly in phase 1 it would be different, right? Because there is no concept of spoke-to-spoke communication in phase 1. All right. Tunnels do get created. Encryption, and you'll see actually encryption is actually an optional configuration. And for the most part, in a lot of our initial configurations, we're not going to focus a whole lot of attention on encryption. We actually want to kind of avoid using encryption because then we can't do our packet captures and we can't identify what the GRE encapsulation looks like on the tunnel packets and the secondary IP header. So we're going to avoid using encryption for a while, but eventually we'll go ahead and layer the encryption on top of DMVPN so you guys can see how that works. All right. Like I said, we are creating these on-demand tunnels. So we need to have a way to do the resolution. Just like ARP for Ethernet, where I resolve a known IP address to an unknown MAC address, or just like inverse ARP for frame relay, where I'm mapping a local DELC, a data link connection identifier, to a remote IP. We have similar resolutions that have to take place in frame relay. Right? In frame relay. I was just talking about that, sorry. In DMVPN. The protocol that we use possibly in frame relay would be some sort of LMI protocol to build the local frame relay connections and establish the encapsulation. And then beyond that, we use like inverse ARP to send messages across the tunnel to identify who is located where. All right? So when we establish our DMVPN initially, it's always going to be a hub and spoke, which is an always-on configuration. And then we use other components like traffic patterns, for example, would trigger some sort of spoke-to-spoke tunnel configuration or spoke-to-spoke tunnel establishment. Okay. We maintain those tunnels based on traffic patterns, so spoke-to-spoke tunnels can stay active for a period of time, but they can also, go down after a while. Control plane scaling means that we only need to have associations or tunnels with the endpoints that we're talking to. Now that could be security associations if we are running IPsec between our spoke-to-spoke devices, but that spoke-to-spoke traffic again is only on demand. The spoke-to-spoke lifetime is based on the traffic only, and I don't recall specifically what the timers are with regard to breaking down those spoke-to-spoke the spoke-to-spoke communication. But I imagine it's a relatively short timer that we can adjust if we need to in the event that we want to do, have our spoke-to-spoke tunnels last a little bit longer. Okay. We do require 2 IGPs, right? We require the underlay routing protocol and the overlay routing protocol. Typically, the overlay routing protocol is going to be a typical IGP that we would run within our enterprise, right? Like EIGRP or OSPF or ISIS or RIP. Although OSPF is one we kind of tend to stay away from because of a lot of the design considerations with OSPF. And again, these are things that we're going to talk about as we start to get into some of our later discussions with regard to DMVPN. All right, we can run, like I said, IPv4 or IPv6 as either our overlay or underlay protocol. We can run IPv6 over IPv4. We can run v4 over v6. But in the end, we still have two primary components to our DMVPN topology, the hubs and the spokes. The hub is referred to as the next hop server, the spokes or the NHS. The spokes are going to be referred to as our next hop clients or NHCs. And whenever those spokes come online, assuming we've applied the appropriate configuration to those spoke routers, they're going to register with the hub dynamically, and they're going to identify their VPN address, which is their publicly facing IP address, and they're going to register their NBMA address, which is the overlay VPN address, which is the one that's usually tied to the tunnel interface. We'll see this in action as we get into the next few sections here and we start doing our configurations. Okay, let's see. When these spokes come online, and I'm going to demonstrate this, we'll take a look at some Wireshark captures and see this process taking place. But when the spokes come online, they are going to register with the hub, and they're going to tell the hub about the mapping that they have, like I said, between the underlay and the overlay address. It's very important for the exam that you guys understand how we distinguish the difference between those addresses, especially on the lab, because it's going to be a little bit confusing on the lab, potentially, because Cisco has gotten away from using public address space to define internet-based connectivity. So in a lot of cases now, you'll see a lot of the documentation, or you could potentially see on the lab that they're using RFC 1918 addresses for both the underlay and the overlay network. So it's difficult to distinguish between what is private and what is public. So it's very important that you guys understand. We'll take a look at this in the captures, but it's very important that you understand the difference between the underlay IP address, which is called the VPN address, like I mentioned, and the overlay IP address, which is called our NBMA address. I'm not sure why they termed it as NBMA. NBMA traditionally has always been kind of defined as like a frame relay type network or ATM or some other network that is multi-access but doesn't support broadcasting capabilities. I get the multi-access point because obviously with multi-point GRE we do have the capability of running multi-access networks, but the non-broadcast piece I don't quite understand because GRE natively supports multicast and broadcast because it simply encapsulates that traffic into a unicast tunnel. So maybe that's it. Non-broadcast meaning that the tunnel interfaces themselves are unicast only. And then we're just encapsulating the broadcast and multicast inside of those unicast packets. We'll just go with that. That sounds like a good idea. All right. So Nhrp, the next hop resolution protocol, is going to allow us to bind IPs to IP. How do I route traffic to the private address, and how do I get it to the next hop device, right? The next hop self is going to tell the clients, or next hop self, sorry, the next hop server is going to tell the clients when you want to send traffic to a specific spoke, what is their VPN address, what is their underlay address, what is their overlay address, and so on. Okay. Ultimately, for the overlay network, that's where we're going to be exchanging our IGP routing information over the tunnel interfaces. Most cases, we're either going to run EIGRP or BGP. The problem with OSPF is there are flooding domain design restrictions We end up having to create a fairly large failure domain or flooding domain in the OSPF design options. All right. So how does the spoke-to-spoke routing work? Spokes obviously initially are going to form an adjacency with the hub. Spoke 1 might know about Spoke 2's routes, which are going to be exchanged via the IGP routing protocol that's running in the overlay network. But those routes are going to be learned via the tunnel to the hub. There are never any adjacencies between the spoke routers regardless of the DMVPN phase. Because DMVPN does not allow multicast spoke-to-spoke communication, there's no way for us to establish neighbor adjacencies between the two spoke routers if we're running a dynamic process. It's okay though, because typically we want to maintain the control plane functionality at the hub and then allow the data plane functionality to pass from spoke to spoke. Okay. The next hop is Spoke 2's VPN IP address if it's DMVPN phase 2. So let's say, for example, Spoke 1 wants to talk to Spoke 2. The next hop is going to be Spoke 2's VPN address. We may just have to do some sort of query, an Nhrp query to the hub router to find out what the VPN address is and how it maps over to the NBMA address. The next hop is always going to be the hub for the next hop for the is going to be the IP address for the hub in DMVPN phase 3, and we'll take a look at that part of it as well when we get into we do have a chapter dedicated or a lesson dedicated to DMVPN phase 3 and its functionality. All right. So I'm going to sketch something real quick just to kind of give you guys an idea of how to visualize all of this stuff a little bit later on. And then we're going to take a look at this in our physical topology and see how we can apply some of this configuration in our physical topology. There is a key difference and a distinction here between a multi-point tunnel and a multicast tunnel. All right. When the hub sends traffic to the spokes, it's always going to be unicast. This is going to include any of my IGP packets. My IGP packets are the multicast hellos and the updates and the queries and the replies and whatnot, depending on the routing protocol that we're running. But we're going to encapsulate those multicast packets inside of GRE. And then that's going to be carried over the GRE tunnels as unicast traffic. So the reason why I mention this is because we can reach upper scalability limits based on the number of spokes that we have, because the hub is going to have to duplicate a lot of the information to those spokes based on the utilization of these unicast tunnels between the locations. All right. So it's not a limitless scalability option. And we can certainly design in a lot more functionality. Towards the end of our lesson today, I'll show you, some of the considerations with regard to DMVPN phase 1 and reachability, and send a best practice design model if we're running just DMVPN phase 1 with spoke to hub and spoke, traditional hub and spoke topologies. When the spokes want to route traffic to each other, that's based on the routing design, and it will also change depending on the DMVPN phase that you're running. There are some cases where spoke-to-spoke communication may not be supported, either because you're running DMVPN phase 1 or because of how you've decided to deploy your overlay network, right, and your routing protocol, right? With disinspector protocols, for example, there is going to be on the control plane functionality, there is going to be a split horizon consideration, right? And we have to either disable split horizon or we have to design around it in some way if spoke-to-spoke communication is necessary. All right. Like I said, routing adjacencies are only formed with the hub. There does need to be some sort of resolution in order to be able to identify the spokes. And there also has to be some sort of resolution between the public and the private addresses in the topology. So let me grab our diagram here, and I'll use this kind of as our sketch diagram to kind of demonstrate some of these concepts. All right, so let me go ahead and grab that topology. So this is our Dmvpn topology. I used some documentation online to kind of build out this kind of a similar topology, not the same, but similar topology. We're not really carrying over any information from some of our previous discussions because it's not really necessary, right? We're going to take a look at how the overlay routing protocols work in this topology, but for the most part, we just have a basic configuration, right? So we've got these loopback interfaces on each of the routers to demonstrate or to kind of create these LAN networks that we want to have reachability from. So clients in the 10 subnet might be trying to reach clients in the 30 subnet or the 20 subnet and so on. In addition, we have our underlay network. This is our underlay network, 209.165.200.240. Now keep in mind, in this case, just for simplicity's sake, because I didn't want to have to build an internet, if you will, these are all point-to-point Ethernet or point-to-multipoint Ethernet connections. That cloud is actually just an Ethernet switch. So these guys do share a common subnet. Obviously, that's not going to be very likely in a real Dmvpn solution. Each of these physical interfaces could be different types of circuits. They could have different IP addresses. Most likely they would. They could be in different broadcast domains. And the cloud could be the internet or some other service provider managed VPN. So we're not running a reachability, network layer reachability protocol on the internet, if you will. But that doesn't change the overall design and the overall implementation of Dmvpn. All right. We also have documented, even though they haven't been configured yet, the overlay tunnel interfaces that we're going to use on each of these routers. Doesn't have to be publicly routable because we're using encapsulation to identify reachability to those destinations. So it doesn't have to be publicly routable. And on top of that, they share a common subnet because we are in effect creating this point to multipoint topology. This hub and spoke from the control plane perspective, a hub and spoke point to multipoint topology. So to kind of use this diagram to reference some of the terms that we talked about before, this is my next hop server. These are my next hop clients. These are my NBMA addresses, and these are my VPN addresses. This is the underlay, and these guys would be the overlay. All right. So that's how we kind of break down each of the components of our Dmvpn solution. And by the way, those terms all apply in any version of Dmvpn. All right. Should be a way to kind of clear all this out at once, but that's okay. All right. So Nhrp. So again, we're going to kind of just table the idea that IPsec is somehow part of this because IPsec just is kind of the final piece that we end up adding to the overall topology. So let's assume that that's going to be there eventually. So our focus primarily is on the attention of creating these GRE tunnels and then identifying how we can create this routing between these different networks. So I might have route network A in this case, and this is network B, and this is network C, and this is network D, and I want to have reachability, right? So the goal here is to establish this GRE tunnel between these two endpoints. We're running some sort of multi-point GRE on this router. That's where Dmvpn comes into play, because if I didn't want to use Dmvpn, I could take that out and I could just create 3 different static GRE tunnels and then set up some routing between those GRE tunnels and make sure they're on unique subnets and so on. So we're actually going to create these multi-point interfaces, all GRE going up to the hub. All right. So this again is my next hop server, and those guys over there are my next hop clients. As far as what I'm running on the underlay network, it could be static routing, it could be BGP routing, it could be some other routing domain, right? Then this cloud could be IPv4 or IPv6. And then on top of that, we run our overlay protocol, which could be, in this case, EIGRP as our overlay protocol. All right. So these spokes are essentially going to establish communication with the hub. All right. Let me get rid of all this. The spokes are going to establish communication with the hub. The hub does not have any specific configuration for the spokes. There is a general configuration that might include some sort of authentication, some sort of ID, yeah, and some IP address information. All right, and we're going to see this in operation. We're going to see how the spokes call home, how they establish their communication to the next hop server, how we can verify that in our command line configuration, and so on, right? Now, if it's spoke-to-spoke communication, there is no direct communication from R1 to R3, for example. We're learning about these network prefixes through the overlay routing protocol. So I do recognize that those overlay networks, that those LANs exist behind the routers. And the next hop IP address, we'll take a look at this as part of our configuration. But the next hop IP address for those destination prefixes is actually going to reference the hub in a lot of cases. It will change depending on the DMVPN process, right? Or the phase that we're using. But for the most part, we're going to point to the hub. Now, in DMVPN phase 1, that traffic has always got to pass through the hub and go to the spoke. We have to do our encapsulations here, and then we do our decap here, and then we're going to have to do our encap again, and then we're going to have to do our decap on this side. It's just not very efficient in that particular case, right? So I'm trying to see if there's a way to erase the whole thing. I don't think so. It's unfortunate. That's okay. All right. I'll look at a different tool later on. We could do that in Paint, of course, but anyway. All right. So now when it comes to communication from spoke to spoke, that's where we have the dynamic resolution by sending over an Nhrp resolution request from the next hop client to the next hop server. And then the next hop server is going to respond with some sort of mapping of the VPN address to the tunnel source, the MBMA address, and then that spoke-to-spoke tunnel is going to get formed to allow that communication to take place. The hub is only going to be used for control plane exchange in a lot of cases. Not every case, but in a lot of cases, and with an optimal design scenario, we do want spoke-to-spoke communication so that the data plane is traveling over the appropriate network interfaces for the most efficient implementation. That spoke-to-spoke data plane traffic might actually flow through the hub initially, and then the hub will send an Nhrp redirect message to the spoke to indicate to the spoke a better way to communicate. Again, this is going to depend on the type of DMVPN that you're going to run, the format of DMVPN you're going to run, and so on, at a different phase, I mean. In the last lesson, we did talk about the Nhrp, what are the important messages. We can kind of review that again, and we'll take a look at some of the important messages a little bit later on as well in our debugs when we do our implementation. Right? We have an Nhrp registration request that allows the spokes to register their MBMA and VPN IP addresses to the next hop server. And that's what's going to be required to allow us to build the spoke to hub tunnels, which are permanent. Then we have an Nhrp resolution request message, where the spoke queries for the MBMA to VPN IP address mappings of other spokes on an on-demand basis, and allows us to communicate to those spokes directly. And that's what's the Nhrp resolution request is really what's going to be necessary in order for us to be able to do the spoke-to-spoke communication. So we may not see actually Nhrp resolution request messages for like a DMVPN phase 1 environment. All right. We also have the Nhrp redirect message, which I just referenced recently. The Nextop server is going to answer to a spoke-to-spoke data plane process. It's going to say, oh, you're trying to create this data plane connectivity from spoke to spoke, but you're sending the traffic in the same interface that I'm going to send it out of. And the hub is smart enough to recognize that that is not a efficient mechanism for communicating. All right. All right. All right. So essentially with this Nhrp redirect message, the Nextop server is telling the spoke, look, I no longer need to be in this data plane transaction. So you guys need to talk to each other directly. All right. Now this is only going to be a function of DMVPN phase 3 to build that spoke-to-spoke communication. In DMVPN phase 2, there is no concept of Nhrp redirect. And you might think about that and say, well, wait a minute. That seems like that should be a basic function of, it seems counterintuitive, right? That it's in DMVPN phase 3, but it's not in DMVPN phase 2. And it has to do with the fact, because the redirect option doesn't really seem like it should be very efficient, right? So it seems like we're introducing this inefficiency in DMVPN phase 3 because of the redirect function. But here's the key. Summarization, default routing, route optimization is not available in DMVPN phase 2. And the DMVPN redirect is what allows us the ability to handle things like summarization and default route injection and so on. So that was actually added so that we could also include some of the more efficient, scalability options that we would typically see in a network based on route summarization and so on. Okay, the implications are going to be important because all of these different considerations that we talk about and all the different elements of design that we talk about are specifically related to routing protocol design. So that's why it's very important that you have a general understanding of what are some of the concepts of routing protocol design that you need to consider. All right. Can we support summarization? Can we support concepts of default routing and optimized routing in order to establish the best possible routing domain that we have, right? In the case of EIGRP and BGP and Nhrp, it's not a problem, right? And it's not a problem because it's something that I lost my train of thought there for a second. Sorry. It's something that we don't really concern ourselves with regard to EIGRP and Nhrp and BGP because they don't have a specific hierarchy that they have to follow. They don't have the leaf spine leaf topology that's required with OSPF. So when we're doing these types of designs with OSPF, that's definitely a much larger concern with how we decide to implement the overall design. Because the topologies in EIGRP and Nhrp and BGP, well, they're just arbitrary. That's why we can do summarization wherever we want. We can do, kind of default routing wherever we want, and so on. So those are some of the considerations to take into account. All right. So that was just kind of a basic introduction, and that concludes kind of that first lesson, if you will. But now let's go ahead and get into the idea of what is the basic configuration, and then we will get into, again, a discussion about the variations of DMVPN, and what are some of those considerations. So I'm going to actually go ahead and pause the video now, actually stop this video, and we're going to get into our next video, which is our DMVPN configuration video. So we'll see you guys.